Hi, welcome back to my class on UVVis spectrophotometry, spectroscopic technique, class number 5. Myself, Dr. Prasad Puthiyillam. I have already 4 classes on, three classes on UVVis spectrophotometry, including first introductory class on spectroscopy, already available in my YouTube channel, My Intuition. Please watch all the videos and put your comments below the description box or comment box. Now this particular video, it is for explaining the Woodward-Fieser rule for alpha beta unsaturated carbonyl compounds. Okay, so Woodward-Fieser rule already we seen in my previous video. Now for alpha beta unsaturated carbonyl compounds, how this Woodward-Fieser rule is applied. How what values they given to predict the lambda maximum for different alpha beta unsaturated compounds. Now why the slide is not moving? Okay, it's moved. Okay, so there are different types are given, in which some are the parent values and some are the increments. Okay, so increments based on the presence of that we need to add. So if it contains alpha, so COR, here this oxygen is double bonded with that carbon, so it is a carbonyl compound. C double bond of R having a unsaturation at the alpha position, double bond at alpha position, alpha beta unsaturated. So if it is CO or alkyl group or even ring residue is there, that means cyclic structure is there, then base value is 215. If it is COH 207, or if it is COOH acid functional group present, or if it is alkyl substituted acid present, alkyl substituted acid is present 193. So it is actually decreasing till here. Okay, now if double bond and carbonyl group in a 5-member ring, double bond is present, that is a carbonyl group, and if it is a 5-member ring, then it is value is 202. Now increment for exocyclic double bond plus 5, endocyclic double bond only for 5-member ring and 7-member ring. That too in 5-member ring, cyclopent 2-enone is excluded. That value is plus 5. Double bond extending conjugation plus 30, homo and conjugate diene plus 39. And if the substances are present at alpha position, beta position, gamma position, delta or higher positions, the values are also given here. So from that, I can guess that if a substitution is present at gamma position, alpha position, what value can be added? If it is beta position, what type of values we need to add based on the substituent present in that. Okay, now we'll take some examples. We have to take a lot of examples to understand this or to recall this table. Then recalling, we'll do a lot of examples, similar type of examples with a double bond oxygen and a double bond that present at the alpha beta position. So here it is a carbonyl compound with alpha and beta positions indicator. Okay, so alpha position and there is a alkyl group, CH3 group, that is it is type of a COR alkyl group. R group is there. Therefore base value that you have to consider as 215 nanometer. Now there are substitutions. Methyl substituent present at beta position or alkyl substituent present at beta position. If it is beta position, we need to add 12 as increment. So 2 beta substituents, alkyl substituents present. Therefore 2 into 12, that is 24. Now total calculated value 239 nanometer. So it is very easy for this compound. Now cyclic compounds are given, but still the we need to identify the carbonyl group. This is the carbonyl group, C double bond O. Then alpha position carbonyl compound, as well as it should have unsaturation at alpha and beta. So we are discussing only alpha beta unsaturated cases. Therefore alpha and beta position. So this is alpha position. You cannot treat it as alpha position. We need to have a double bond in conjugation. Then only this particular table we can follow. Therefore alpha and beta position having double bond, and this one we can represent as alkyl, or it is actually a ring residue. We consider as ring residue. Therefore it is double bond CH that also got replaced. Substituent is there. So double bond single bond C, double bond O, single bond R. So it is the same 215. So the basic value, it is 215 nanometer. And there are alkyl substituents at alpha position. So one alpha substituent, alkyl substituent, 10 nanometer. Now one more substituent is present at beta, that is a ring residue, not substituent as such, we call it as a ring residue. So a ring residue is present at beta position. Therefore, beta position value it is 12 nanometer. Therefore, add all those 215 plus 10 plus 12, it is 237 nanometer. Okay, now there is a bromine substituent, Br is added at alpha position. Okay, so this is again alpha beta unsaturated carbon, and R group is, or I'll say the ring residue represents R. Therefore, it is base value is 215. Base value it is 215. And we have the bromine substituent at alpha position value it is 25. There are alkyl substituent, it is similar example of previous one. Okay, so the beta alkyl residue or ring residue is present, which is value 12, calculated value 252 nanometer. Another structure in which a carbonyl group is there, C double bond O, unsaturation alpha beta unsaturated compound unsaturation present at alpha position. So this is alpha, this is beta position. So alpha beta position, and it is again alpha beta unsaturated carbonyl compound, and R represents the ring residue or ring substituent is present. Therefore, it is considered as R. Therefore, base value again it is 250. Base value is 215, and there are alkyl substituent or a ring residue substituent, a ring residue and all. So at alpha position, one ring residue is present here. At beta position, 1, 2, 2 ring residue present at beta. Okay, therefore one alpha is there, 10 nanometer, and there are 2 beta. This is 2 into 12, 24 nanometer. We need to add as increment. And this double bond, it is exocyclic double bond plus 5 value we need to add. How many exocyclic bond? To this cycle also it is exocyclic. To the first cycle which containing the double bond also it is exocyclic double bond. Therefore 2 exocyclic double bonds present. Exocyclic double bond 2 into 5, that is 10 nanometer we need to add. Therefore calculated value is 259 nanometer. Another structure which C double bond O is present here. So alpha beta unsaturation also therefore this is alpha and beta positions, and R we call it as the parent value is 215. It has got a double bond extending conjugation. So this much is we consider as alpha beta unsaturated carbonate, and after that one single bond and double bond. That means conjugation is extended. The double bond is present, extending the conjugation. Therefore, we need to add plus 30. So 30 nanometer. Now substituents, alkyl substituents or ring residues. Okay, alpha position there is no substitution. Beta position we have one. Then what is this? Alpha, beta, gamma, and delta. Okay, so delta also have one. This one first we'll consider the beta case. One beta ring residue is there for 12 nanometer. and alpha, beta, gamma, and delta position also one present. So if it is delta position, okay, it is delta position, this should be 18. Anyhow, it is plus 18 only. So ring substituent at delta position, any one mistake will be there in my video. Okay, so at this position, delta having one ring residue, therefore it is not under gamma. Don't get confused. Here correction is there. Okay, so it is 18. It should go there. Okay, so anyhow it is 18 only. Okay, therefore one delta having 18 nanometer, and this one double bond it is exocyclic. It is exocyclic to the second ring. So from here, if you look, it is exocyclic double bond. Now, what is exocyclic, endocyclic? That is also explained in my previous video. You just go and refer it. If you not confused with this, what you mean by exocyclic. Okay, so here one exocyclic ring, exocyclic double bond present. Therefore, we need to add 5. Total calculated value 280 nanometer. Now, what is this? Okay, we have 2 double bonds present, and we can consider this also alpha beta unsaturated carbonyl. Here also it is alpha beta unsaturated carbonyl. That means both sides conjugation is equal to cross conjugation. So cross conjugated system, what we need to do? So cross conjugated system, we need to identify the most highly substituted. So we'll see. So here one substitution, let me put a mark there. Okay, so one substituent or a substitution present there in that side, if you consider. The other side, if you go, okay, so differentiated with the 2 different color. So this is green color, I think this is orange color. Okay, so here at this particular way, if you go, it has got one substituent. This particular way, if you go, it has got a 2 substituent. Therefore, most highly substituted alpha beta unsaturated carbonyl will be considering. Okay, therefore this one we will consider. Okay, so consider it. Look, the shape looks something different. Okay, so this we are considering. Okay, I'll close it here. Okay, I cannot close it further. So alpha position, beta position, and beta position having substituent. And this particular carbon we consider as the alkyl group R group. Therefore, base value anyhow it again it is 215 only. So no variation in that. It is 215. Double bond extending conjugation case. Okay, it is not there. You may confuse. That's why I'm giving that example. So after giving this example, you don't do the mistake. Okay, so this double bond, it is not extending conjugation. This is separate double bond present. It is not a part of this conjugation. If it is present here, that means it becomes a this position where the green dash is given. At that position, if double bond was there, means that is an extending conjugation. Okay, so here it is not an extending conjugation, double bond extending conjugation. It is absent. Cross mark I put here. Okay, so it is not there for this compound. Okay, then next to doubt whether it is having endocyclic double bond, whether it is endo, same ring double bond is there, but it is not again it is not what we call as conjugated, as well as it is not only this value have to give only for 5-member ring and 7-member ring. This is a 6-member ring. You can count 1, 2, 3, 4, 5, 6. Okay, by seeing the structure itself, we know that it is a 6-member ring hexagon. Even kids at class grade 1 or UKG itself, they know what is hexagon, a 6-member ring. So only for 6-member, 5-member ring and 7-member ring, we need to consider this endocyclic double bond case with explained by Woodward and Fieser, not me. Okay, so we have to cross it. That is also not applicable here. So we no need to consider all those. But substituent alkyl or ring residue we need to consider. Already we indicated that at beta position we have 2 ring residues. That is beta value, it is 12, so 2 into 12, 24 nanometer. Need to add. Now exocyclic, it is exocyclic bond is present here. So this double bond is exocyclic to the second ring. Okay, therefore 5 nanometer will add. So calculated value is 244. 244 nanometer. Now WoodwardFieser rule for aromatic compounds. I'm not going in detail about all aromatic compounds. For Woodward didn't given. I didn't get from the literature about remaining. Acyl benzene we are discussing aromatic compounds. Acyl benzene is an aromatic compound. Acyl benzene. Acyl means a C double bond or group present in that. C double bond or R group present. We call it as acyl group. Now the parent value, even if it is C6H5COOH or C6H5COOR, the value is 230. If it is C6H5COR or R, in which R is alicyclic residue or even alkyl group present, then also value is 246. If it is C6H5 C double bond O single bond H, that is aldehyde functional group, then also it is 250. So this is ketonic functional group, and last one it is aldehyde functional group. So 230, 246, 250. Now, to addition to that increments, okay, so in benzene ring, when we say it has got ortho position, meta position, para position, what is that? I'll explain when we take the examples. Okay, so if the increment due to oxochrome or the substituents at ortho position, if it is chlorine 0, 0 and plus 10, if chlorine is present at ortho position, no need to add any value. If chlorine is present at meta position also, no need to add any increment in nanometer while predicting the lambda maximum. So I'm explaining the prediction of lambda maximum given by Woodward-Fieser rule. For Woodward-Fieser, and the rule is plus Woodward-Fieser rule, and this is for aromatic compound or acyl benzene as an example. Okay, so the remaining all it is given almost its first column ortho case I put it in the increasing order. Okay, so second column accordingly it is increasing only that oxygen case, oxide ion case, it is plus 20 here, and remaining are increasing. So here it is some variation is there. So we can see that even at a para position, some value difference, large difference is there compared to ortho and meta position. Para position, if substituents are present, it is contributing more towards the lambda maximum. Why so? That also explained in my video classes, not under UVVis spectrophotometry. Under organic chemistry, explained that if the substituent is present in para position compared to the original functional group, the para position substituents will not impart any steric hindrance, or it may support or support contributing the electrons, or it will be contributing withdrawing the electrons. Whereas if it is at meta position in benzene ring, the resonance stabilization in which the meta position is not participating as such, the any substituent at meta position will not participate as such. Whereas if it is ortho position, then also it will support in electron withdrawing or electron donating type groups. If it is there, it will be supporting the resonance. And if ortho position also has got some type of steric hindrance to the original functional group, therefore considering all that, and this also we have as an example, it supports that whatever information we have. Okay, so we can see that para position, if substituent is there, more values we need to add compared to the substituent at ortho and meta position. Now, example, okay, benzene ring connected to C double bond of CH3 is a ketonic functional group. Okay, so see acyl group it is present, so this is acyl group. Okay, so that is we need to consider acyl group 246. Okay, so that is C6H5COR type, therefore base value is 246 and ortho positions. So now consider this as the main functional group. Ortho positions are the nearby carbon present in the benzene ring, and meta positions as well as one para position. Only one para, two meta, two ortho. Now substituent at which is the substituent? Now chlorine is a substituent and it is present at para position. Therefore, if it is, since it is in para, we have to add 10. If it is ortho or meta position, it is 0 increment. Okay, so for this para position, we will giving 10 increment. Okay, so chlorine at para or para chlorine 10 nanometer we will be adding. Calculated value 246 plus 10, 256. Okay, now same type example, but instead of chlorine we have a hydroxyl functional group present at para position as well as the meta position. Okay, so base value 246, ortho position, meta position, para position. Hydroxyl group present at ortho position, 7 only, plus 7, or not ortho position, meta position. Okay, so plus 7 we need to add for the hydroxy meta 7 nanometer increment. Now again it is present at the para. Oh, we need to add 25. So 7 to 25. the para effect. Okay, so hydroxyl present at para position 25 as increment, calculated value 281 nanometer. Another example, methoxy functional group also present, carbonyl functional group it is present here, and this is the ring residue, alicyclic residue. Okay, so for alpha position, beta position, or alpha position, this is alpha beta also, but we are considering it as a benzene ring case. We cannot treat as alpha beta because in case of benzene, the double bonds have a different nature. It undergo resonance stabilization. These electrons are continuously in movement. Okay, therefore this is the functional group that we consider. It is giving that C6H5COR case, that is 246. Now ortho and para position, how to identify. Okay, usually the functional group present at benzene ring, we consider it as the parent functional group, and remaining positions we consider as ortho, meta, para. So here this case, since it is alicyclic group present and functional group present on this particular side. Okay, so here this side at this position, we consider this as the origin and these are the ortho positions. Okay, so ortho positions, two ortho positions, two meta position, one para position. Now let us guess. So let us check the substituents. What are the substituents? Anyhow, CH3O, it is clearly visible. CH3O, that is which phase it is. Which one? OR. Okay, it is OR. Methoxy group or alkoxy group. Now at the ortho position, a ring residue is also present. Alkyl substituent considered as alkyl or ring residue. I forgot to write that ring residue. So here you also add alkyl plus ring residue. Okay, so the ring residue is present at ortho position, plus 3 will add 3. Then at OR, that is CH3O substituent present at para position, that is 25 nanometer, we need to add calculated value 274 nanometer. Applications of UV visible spectrophotometry in general. Detection of functional groups, it can be used. Extended conjugation, or to identify the presence of extended conjugation also we can use. Okay, distinguishing between conjugated and non-conjugated compound, that distinction can be done with the UV spectrophotometry. Identification of unknown compound, that is anyhow we know that it is used. Examination of polynuclear hydrocarbons. Elucidation of structure of vitamins. Preference over two tautomeric forms. Identification of a compound in two different solvents. Determination of configurations of geometrical isomers. To distinguish between equatorial and axial conformations, and etc., etc., and etc. So many applications are there. You can refer many textbooks, different applications you get, but all are having almost the same information. But many important applications are there for UV visible spectrophotometry. I took only 10 I took from the textbooks. Okay, so the absence of a band at particular wavelength may be regarded as evidence for the absence of a particular functional group in compound. So clear. If a functional group is absent, then corresponding absorption band will not be there. Therefore, we already know many UV spectrophotometry readings we have, many functional group, what should be the expected value we have. If that expected value, if it is not there, means that expected functional group, it is not there in the compound. Therefore, we can detect a functional group whether it is present or not. Even for some complicated molecules, as such many information we may not get, but many required information can be collected from UV visible spectrophotometry. A simple case, if I say, if within this 200 to 800 nanometer range, if a spectrum, if the compound is not giving spectrum, or this spectrum is transparent, there is no peak present in our after doing the analysis, that can be used to get the information that conjugation is absent, or a carbonyl group, aldehydes and ketones are absent. Benzene or aromatic compound, it is not a benzene or aromatic compound. It does not, the compound does not contain bromo or iodo atoms. Extent of conjugation, that is in polyenes mainly. Polyenes means in which the CH double bond CH repeats n times. That means R CH double bond CH, single bond CH, double bond CH, single bond CH, double bond CH, like that, etc. goes on. Okay, so and at the end again CH3 is there. Okay, so that is the general representation of a polyene. Increase in number of double bonds shifts the absorption to longer wavelength. That means more double bonds are present, more pi electrons are present. More pi electrons will undergo what we call as mixing. Okay, that is explained in my UVVis spectrophotometry class videos. Just go and check that. Okay, so it undergoes mixing. Why conjugation supports the visible or UV visible light absorption? Because those pi electrons will participate in interactive way, or it is a destructive mixing also there, constructive mixing also there. Because of that, pi orbitals constructive destructive mixing and pi star anti-bonding orbitals mixing, the energy difference between the highly occupied molecular orbital and the low unoccupied molecular orbital the difference will be less. Because of that, very less energy is required for the electron to jump to that higher energy level. That means less energy means higher the wavelength. Okay, so it shifts to longer wavelength. So if n value is 8 or more than 8, such polyenes are colored. Now, distinction of conjugated and non-conjugated compound. An example is given here. So this is having conjugation, C double bond O, that double bond, single bond, double bond. So it is in conjugation. Okay, so this is one of the conjugated structure. Here it is double bond, then double bond. Therefore, conjugation it is absent. It is not there. Conjugation is not there. Same molecule, same number of carbon atoms, same number of hydrogen atoms, same number of functional group. Therefore, we can call it as a isomer. So these two are isomers, structural isomers, and this particular structure, it is not having conjugation, non-conjugated compound, and first one it is a conjugated compound. So conjugation, if it is present, and again oxygen heteroatom is there, oxygen having lone pair of electron, the n pi star transition. Okay, because of the lone pair of electron, it can jump to the pi star state. Okay, so this pi is in bonding state. If this separates and goes back to the, it become anti-bonding. If they repels, it become anti-bonding. Therefore, that is the anti-bonding orbital, imaginary orbital that we, and this electron can go to that imaginary orbital pi star state, and it appears at a longer wavelength. N pi star transition is possible if conjugation is there and shows a absorption band, but having longer wavelength, at a longer wavelength. Then conjugation is absent in this case, shorter wavelength absorption compared to previous compound. Note it down. Next, identification of unknown compounds. Identification can be done by comparing with the non-compound spectra. That means already if you know the compound, identified compound, note down its spectra or take the print of that spectra, keep it as a reference. Then for other unknown compound spectra, compare with that, very easy method. Now, examination of polynuclear hydrocarbons. Polynuclear means with two or more closed rings present. Benzene and polynuclear hydrocarbons have characteristic spectra in UV region because of, again, conjugation is there, alternate single and double bond, and aromatic nature, the pi electron, pi to pi star possibilities are there. And if it contains any heteroatom, then n to pi star is also possible. Okay, so polynuclear hydrocarbon, that means with two or more closed rings. It may be fused one or extended ring if it is present, also we call it as polynuclear hydrocarbon. The presence of substituent in the ring also shift absorption maximum to longer wavelength. That also we see in the examples, WoodwardFieser Rule also we see for aromatic acyl benzene, substituent present in the benzene ring, we have to add an increment. Okay, so for the presence of substituent also shift the absorption maximum to longer wavelength. Longer wavelength means lower energy required, less energy required to get the spectra to observe the photons. Now, elucidation of structure of vitamins. Example, vitamin A1, then vitamin A2. Okay, so vitamin A1 structure I am drawing. So a hexagon required, then tish means this and this bond. Okay, so many dish we needed. It is a vitamin, a complicated molecule, a little bit, not that much complicated. Okay, so one dish bond is given, another this. Okay, how many we got? We got 1, 2, 3, 4 peaks. Okay, so 4 peaks required. Then another alkyl substitution at second peak and alkyl substitution at fourth peak, and one CH2OH. Not done. We have a double bond present inside the ring. That is vitamin A1, and we have so many pi bonds. So pi. Okay, it is not a chai. It is pi. Okay, otherwise it becomes chai. Okay, so it is pi bonds are also present as a conjugation, extended conjugation. So conjugated double bonds it will give color. This is vitamin A1. It will absorb at around 325 nanometer. Okay, so vitamin A1 to vitamin A2. What is the difference? Okay, so this 1, 2, 3, 4, and 2 alkyl substituent and CH3 substituent, and 1 CH2OH, a double bond present. This is vitamin A1, already seen. Pi 4, 5 bonds also present. This is vitamin A1, not the previous one. So this is vitamin A1. So vitamin A2, that difference. Okay, I'm adding one more double bond here. Okay, so here one more double bond added, it becomes vitamin 2, and with that extra double bond, the absorption is entirely different. It absorbs at approximately 287 nanometer, then at 351 nanometer. 2 peaks are obtained for vitamin A2. Therefore, by that we can explain or elucidate the structure of vitamins based on the spectrum obtained, absorption spectrum obtained. Now, preference over tautomeric forms. What is tautomerism? Okay, for example, 2-hydroxypyridine. Okay, so 2-hydroxypyridine. So this is pyridine structure. Benzene ring containing one heteroatom, nitrogen as heteroatom, and there is a hydroxyl functional group at position 2. So in heterocyclic compound, the heteroatom we give the number 1, 1, 2. Okay, we won't call it as ortho, para, meta. Okay, so we call it as 1, 2, 3, 4, 5, like that positions we will give. At position 2, we have one hydroxyl functional group, therefore 2-hydroxypyridine. Tautomerism, it can undergo tautomerism. That means this oxygen, hydrogen can be shifted to nitrogen. Here it becomes a double bond, therefore this double bond will shift. Okay, therefore that tautomerism, it is represented. Okay, so it is represented here, tautomerism. Okay, now the obtained spectra indicates the presence of alpha, beta, unsaturated carbonyl compound. So after taking 2-hydroxypyridine in and taking its spectra using UV visible spectrophotometer, the obtained spectra, it indicates the presence of alpha, beta, unsaturated carbonyl compound. That means this equilibrium, it shifts to right side always. So this is more stable keto form. So this is keto form. This is enol form. Enol form means a double bond carbon with OH, we call it as enol form. This is simple ketone form. Ketone form, that is C double bond O, both side, just like a alkyl substitution R. Okay, here it is not R, it is replaced by N. Okay, therefore this is keto form, this is enol form. So keto form is more stable, and tautomeric forms preference, which is more stable, that also we can, which is more preferred, that also identified by UV visible spectrophotometer. Identification of compound in different solvents. Different solvents, example hexane and water, and the molecule, organic molecule taken is chloral hydrate. What is chloral hydrate? So carbon, chlorine, 3 chlorine, then connected to C double bond O, single bond H. Chloral, this is chloral. Now it is having hydrate. Hydrate means water of hydration. H2O is present. This is not mentioned in whether it is dihydrate or pendihydrate, therefore we consider as monohydrate. So this is attached or near to that a water molecule is present. Okay, always it remains with that structure, okay, for better stability. Okay, or because of this depolarized this trichlorine and then carbonyl group, because of that it is more molar or polar, therefore a water can always stay with that, or we call it as chlorohydrate. Now if it is in hexane, this structure it is possible only in hexane. It shows a absorption maximum corresponding to the carbonyl group. So carbonyl group is present and it shows the absorption that corresponding to the carbonyl group. Okay, again oxygen having lone pair of electron, n to pi star, even pi to pi star also there. Now if it is in water, then this carbon double bond O will not be there, it will be converted as OH because more water present, more hydroxyl, it will attack that carbonyl group and it will be converted as CHOH group. Therefore, their carbonyl functional group is absent and it will not give the absorption maximum spectra corresponding to carbonyl group. Now, determination of configuration and geometrical isomers, trans-azobenzene and cis-azobenzene. You heard about this before? Not heard? Or you heard about this? It is there in my class videos, class number 3, at 34 minutes 35 seconds to 37 minutes to 10 seconds, in that approximately in that ratio explained about this. So please go watch that one and note it down as an example for a determination of a configuration of a geometrical isomers. Move on to that. Distinguishes between equatorial and axial conformation. Okay, what is equatorial, what is axial conformation, we always studied, but still, okay, so it is presenting equatorial. Okay, it needs the hexagon. Okay, so a hexagon, the cyclohexane, and this particular position, if any substituent present, it is equatorial, and these are our axial. Axial means the substituent present which is in the same plane of the carbon. So this carbon present in the same plane, the substituent present, then we call it as axial substituent or axial position. Okay, all molecular in the same plane, whereas equatorial it is away from that. Okay, and then it is represented as E as well as A. So equatorial and axial, now it is clear to you, I think. So if you forgot that, you just recall it. Then I'm drawing one cyclohexane. It is very interesting, so I'll continue. Okay, so two cyclohexane fused case with the carbonyl functional group C double bond of alpha beta unsaturated carbonyl. Okay, so I put a double bond there also. Now one polar group atom, bromine, which is in equatorial position. So it is equatorial, the substituent is at equatorial and its isomer. Very interesting to draw this structure. Okay, this isomer, alpha beta unsaturated case, it is axial. Okay, bromine is in axial position, second structure. Bromine is in equatorial position and the first structure. Now, what is the information we'll get from looking into the structure? Now we can see that this bromine is exactly on the line of that oxygen, or it is in the same, it can participate, it is its electron density contribution, electron withdrawing or electron donating, that you go check. I know what it is. So that is in the same plane, same line. It will affect this pi bond, or it is contributing towards excitation of this pi bond. Therefore, pi to pi star for n, lone pair of electron is present on oxygen. Okay, n to pi star will be influenced by this bromine, which is if it is present in axial way, that is in the same plane of that molecule. If it is present, it will be affecting. Therefore, the n to pi star transition band appears at longer wavelength in alpha beta unsaturated ketone, is influenced by the presence of polar group in gamma position. Okay, gamma position is alpha beta gamma position only. Okay. Pi n to pi star transition band appears at longer wavelength. Longer wavelength means lower energy. So So it absorb a lower energy. If it is axial case, it requires lesser energy for this n to pi star transition, because electrons, okay, from bromine like this in the same way, same line it is. Therefore, at this pi electrons, it becomes easily it becomes a pi star case. From pi bonding orbital can be converted into anti-bonding orbital, or it is state. Therefore, it takes very lower energy for this n to pi star transformation. Okay, so for gamma position, if it is only axial case, okay, so the polar substitution in the axial position shift n pi charge into lower energy. Lower energy is required, or a higher wavelength it will absorb. Okay, so please watch my videos in my YouTube channel. My intuition only. Like the videos and share to maximum. That's about this particular class video. Okay, so thank you very much for watching my video once again, and have a nice day.